Hello, our project is predicting increased weather phenomenon in Hampton Roads. My name is Marian, and I'm presenting on behalf of my team due to our asynchronous collaboration. Our inspiration came from the growing impacts of climate change and the increasing severe weather affecting our community. We aim to investigate how rising temperatures correlate with increases in tornadoes and tropical storms in the Hampton Roads area. Here's the region we focused on: Chesapeake, Hampton, Norfolk, Portsmouth, Suffolk, and Virginia Beach. This image, sourced from the Virginian Pilot, shows flooding in Norfolk, one of many recent examples of climate related impacts. Our project's goal is to use predictive modeling and visualization to better understand patterns of extreme weather and share insights with policymakers, stakeholders, and the community. Our main goal was to determine whether rising temperatures have a direct correlation to increased cyclonic activity, tropical storms, and tornadoes from 2009 to 2024. To explore this, we built a predictive model simulating changes in storm frequency and examined various factors. To accomplish this, we followed the standard data science process: data collection, data cleaning and pre-processing, visualization, exploratory data analysis, and machine building and evaluation through machine learning models. Because inclement weather in Hampton Roads has increased, we focus on two storm categories: tornadoes and tropical storms, including hurricanes. And our findings are intended to support policymakers, stakeholders, and the community and mitigate the impacts of rising temperatures. We use two major data sets. Our primary data set, NOAA Storm Events Database, containing tornado and tropical storm records, and our secondary data set was Norfolk International Airport's daily weather summaries, including temperatures, precipitation, and wind speed. For our project, all work was done collaboratively in Google Colab, and because we were working asynchronously, we experienced recurring file path errors. Jose taught us a helpful workaround to this, and it was creating a shared folder inside Collab's content directory and manually uploading all CSV files. This eliminated file not found errors and allowed the entire team to run the notebook consistently. We began by loading the datasets into data frames, inspecting data types, checking memory usage, and identifying null values. The secondary dataset had roughly 22,000 missing average temperature values, which we addressed by calculating the mean between max and minimum temperatures. We filtered out irrelevant columns and kept only features essential for our analysis. Duplicates were removed, data types were standardized, and outliers were identified. Although there were outliers in wind speed and storm damage values, they were determined to be natural and not data errors. We dropped snow-related fields and kept average wind speed due to its relevance to storm intensity. Only the years 2009 to 2024 were included. Missing data was addressed, primarily with calculated averages, and unnecessary columns were removed. Missing data was categorized as missing completely at random, missing at random, or missing not at random. Most of it was found to be either irrelevant or easily corrected, though future work may benefit from advanced methods to handle the missing data. Next, we prepared the datasets for modeling. We converted date columns to proper date-time format, merged datasets using date as the key, created features such as temperature anomalies, temperature variability, and daily temperature changes. We calculated monthly event frequency and event type counts. And from 2009 to 2024, only two main storm types appeared consistently: tornadoes and tropical storms. Monthly fluctuations appeared to align with temperature variations, supporting our hypothesis. Initial visualizations, histograms of temperature changes, and time series plots confirmed that the clean data was suitable for modeling. In Tableau, we created a heat map showing event counts by year and location, a line chart comparing storm trends across Hampton Roads cities, and a bar chart ranking storm frequency. As you can see, Norfolk and Virginia Beach were the highest. These visualizations formed an interactive dashboard that allows users to explore storm patterns by location, year, and event type. This dashboard makes complex climate data digestible and intuitive. Our goal was to predict the frequency of extreme weather events using regression models. We first used linear regression with features such as temperature anomalies, temperature range variability, wind speed metrics, event counts per month, and the model's performance metrics included mean absolute error, mean squared error, root mean squared error, and root squared. Here's the linear regression model. And the model tended to overpredict at low counts, perform better with mid-range counts, and underpredict with high event counts. This suggested the linear model could not capture nonlinear relationships between climate variables and storm frequency. We then implemented a random forest regressor, which immediately improved performance. Predictions aligned closer to the identity line, then slight overestimation remained for low event periods. We tuned hyperparameters using both grid search and randomized search. Both produce similar RMSE values, indicating stable model performance. Cross-validation confirmed the model generalized well. Feature importance analysis revealed that average temperature was the most significant predictor of storm frequency. Our project demonstrated several key insights. One, rising average temperature is a primary predictor of extreme weather events in Hampton Roads. The frequency of tornadoes and tropical storms has increased, especially in recent years. While correlation is strong, more research is required to determine causation. And lastly, the random forest model provided more accurate predictions than linear regression. Overall, our research supports the growing evidence that climate change is influencing local weather patterns. Future work will focus on incorporating additional data sets, such as humidity, precipitation, or geographic variables, building more advanced machine learning models, collaborating with environmental scientists, climatologists, and policymakers to develop practical mitigation strategies. And our intent of this project is to provide actionable insights that support planning, infrastructure reinforcement, and community preparedness. Thank you so much for listening to our project.